was discussed by the first two people who explained. So if there is anything more you would
Colli-
like to add.
Collisions
Is
with
there
other galaxies.
Sorry?
Collisions with other galaxies.
Collision with other galaxies. Okay.
is it
No,
possible
not really.
the magnitude of the centripetal or the angular momentum must be such that if it's very low, it must be a fuzzy cloud. If it's high, it must be a Milky Way galaxy, something of that sort. Does that play?
Hmm. Yes, yes, it does. It is. It does.
I think the rotation of the galaxy, because not all galaxies rotate at the same speed and even in the same direction.
Yes. Yeah. Well, that is what contributes to the angular momentum of it.
Mhm.
Yes. Yeah. Anyone else would like to add to it, or would we go further?
And there can be one more thing, like it's theoretical actually. Because
Sorry, come again.
uh, I think I can name one more thing, but that's only theoretical as I only thought about it. It's about
All right.
dark matter which acts as a scaffolding for a galaxy. Take it say,
Mm-hmm.
I
How?
mean, the matter present. I mean, it's just a theory that's I've read somewhere. It's about like how matter uses dark matter as a scaffolding. I mean, every galaxy is present in a slump of dark matter.
Right. Yes, yes, that's a very important thought that you can add there. That is part of a reason why it has its shape. Yes, so thank you everyone for your uh, very nice contributions. So we'll go forward and check what are the topmost reasons. Well, here we go. So our two main reasons, because most of our galaxies are either spirals or ellipticals. So for these two, we have angular momentum and merger history as the most important sources or most important reasons for the shape that they acquire. So for spirals, for example, if you take angular momentum into consideration, this is basically a spinning energy, right? So a galaxy will inherit the spinning energy from the gas clouds it forms from. And if the initial cloud from which the galaxy is forming from has a lot of net rotation, like in other words, if it has a lot of angular momentum very high, then the gravity will pull the gases into a very flat disk like projection that will rapidly rotate. Okay. And this rapid rotation will conserve the spin, similar to how like skaters spin faster when they pull their arms in. I think I've already given this example in a previous class. So they tend to pull their arms in when they want to spin faster. So this is what happens when there is a disc-like structure that is rotating very fast, and if they want to stabilize and conserve the spinning energy within them, then they will try to pull into the core of the disk. So this basically disks are very thin and cold, and it allows for a lot of organized and continuous star formations out of these disks. And these formations are of spiral arms, which when further developed into. And let's say if the spin is very high, if the spin is very high of these disks, then it'll mean to a spiral galaxy, simply spiral galaxy. Now we have a subcategory for spiral galaxies as well, that is barred spiral galaxies. All right, so we'll soon look into an image of that in the upcoming slides. But for now, you have spirals and you have barred spirals. So if the spin is very high, it is spiral. And when the spin is comparatively lower, it could lead to a barred spirals as well. That is about angular momentum for spirals. Now, if we take merger history for elliptical galaxies, for example, elliptical galaxies are generally a result of very violent collisions between existing galaxies, as someone has already mentioned. So, like, let's say sometimes there are two spiral galaxies that are colliding with each other. And these two spiral galaxies, when they crash, they have a massive gravitational shock that will destroy all the organized nature of the spiral galaxies. Because I had mentioned in the spiral galaxies, they have a very flat, thin, cold disk that is able to make all the star formations continuous and organized. But what happens when these two flat disks collide with each other, or there's a collision happening between two spiral galaxies? Obviously, the organizational nature or the continuity of star formation, all of that are affected. Now that will just create a big chaos, and the stars and all the gases, all of those get scrambled up into some random three-dimensioned orbits. Now these three-dimensioned orbits have some dissipating angular momentum out of it, and this angular momentum, as it gets dissipated, and it is having a very, what do you say, disorganized nature within it, it creates a sort of a very smooth fuzzy blob like object, or fuzzy blob like nature or projection. And this shape of a very, very fuzzy nature will also create some sort of violence because of the collision, as well as the nature that is within the core, as well as what is happening, all the all the gases and stars being dissociated and deformed, and all the continuity information are interrupted. When all of this happens, there's a lot of heat ejected, and some cold gases are also ejected. So all these will prevent these galaxies from any star formations in the future. And these sort of violent mergers can mean elliptical galaxies, for that matter. So we have two major reasons for spirals. It's the angular momentum, the high spin, causing it to be a flat disk. Now, for ellipticals, it's these high spinned, flat disk spiral galaxies colliding with each other and forming disorganized sort of nature that is causing an elliptical galaxy. Hope this is clear.
Yes, ma'am.
All right, I'll take that as a yes. Thank you. And yeah, so today we'll be looking into, so today we have part one of our galactic studies. And today we'll be looking into the morphology, where we'll be looking into the classification types of galaxies, wherein we'll have elliptical, spiral, barred, lenticular, and SO types. That is lenticular, SO or S0 types. And galactic dynamics will be looked into. We'll be dealing with two major theories there. One is the winding problem, and one is the density wave theory. And then we'll be looking into the invisible universe, wherein we'll be looking more into the dark matters. Okay, so first off, we have this is the Hubble tuning fork. You might have come across or heard about it in somewhere during your astrophysics research or something. This is designed by a person called Edwin Hubble. So he has come up with the Hubble tuning fork to easily categorize between various types or kinds of galaxies based on their shape and appearance. So, so here in this fork diagram, we see three major galaxy types based on visual appearance. And these visual appearance is basically very directly linked to the galaxy's evolutionary history and some internal physics of it. So, okay, I'll just probably zoom this in. So this will be easy for you to understand. So on the left side, we have you can see E0, E3, E7. All these are elliptical galaxies. So this is due to the constraint of space. This actually has different dimensions, as an E0 would be a perfect circle, and E1 is slightly flattened on the poles. E2, E3, E3 is somewhere here. E4, E5, E6, E7 is extremely flat. So just try to imagine all the different stages between E0, E3, and E7. So they look like more or less a giant smooth, cosmic balls. And crucially, they are the result of major merger events that I had mentioned in the earlier slide. So these events, as I've already said, they scramble up all the stars and they result in some random three-dimensional stellar orbits. And compared to the spirals, they have very little overall rotation that is taking place, and they have no cold gases or dust because it was either consumed or ejected during the merger, because it's very violent. All the heat and energy and all the cold gases are all just ejected out during the merger. So due to this ejection, consequently what happens is, they are finished systems, and these finished systems will contain only some old low mass red stars, or no new star formation is basically allowed to happen after all the major collisions that took place. On the right hand side, we have spirals. Now spirals are basically termed as S0, SA, SB, SC, and it goes on to a certain limit. I think till SE it goes on. And barred spirals are basically when it is spiraled, but it has a subcategory. So I don't know if you're able to see it properly. Like for example, here if you see, the spiral is perfect. Okay, there is a perfect spiral from every point in the middle. But the barred, if you see, there is a very small bar that is appearing in the core, and even as we go, the bar just gets more straightened and more prominent. So for that, we have spiral barred A, spiral barred B, spiral barred C, etc. Okay, and also yeah, okay, come here. I'll just finish up spirals and barred spirals before that. So spirals, as you can see here, yeah. Yeah. So the spirals, as you can see here, are they look more flatter, or this one you can take more of, what do you say, a top view. So they are more flatter. They are disk-like galaxies, meaning they have a significant amount of angular momentum going on there, and that confines their motion to a flat plane. And they are the sites of some ongoing star formation, and this is fueled by some, what do you say, humongous amounts of cold gas, dust, etc. Now, the sub-classification A, B, C here you see for the spirals uh, dictates their structure. Okay, so SC types have pretty huge dominant central bulges. Like if you can see, the bulge at the center or the core is pretty thick and dense, and they have more tightly wound arms. Hope that's pretty evident from the image. And while if you go up the line and you see SC for that matter, they seem exactly the opposite, right? The core is not as dense, and then the bulge is not very evident here. And even the arms are very loosely wound. They're very distinct. Okay, they are not very clouded like in SA. So SC has some loosely wound, distinct arms. So Can someone tell me what could be the kind of oh, okay, I'll probably just finish this up as well. All right. So coming to barred spirals are having the exact same nature. It's just that there is a bar formation here because of the rotational differences. Now we have SBA, SBB, SBC, wherein instead of the bulge at the center, we'll be concentrating about how long the bar is. So here, if you checked at SA and SC, the bulge was dominant and less dominant. Here we have the bar that is less dominant for SBAs and more dominant for SBCs. Okay, so this is purely based on the rotational effect of it and the angular moment, obviously. So that is about barred spirals. All right. Also, if you have seen something here, okay, the lenticular, or also called the SO, the S0 or SO, we call it both. So the SO galaxies or the lenticular galaxies are somewhat like a transitional type of galaxies. Like you can see, it's exactly in the middle of spirals and the elliptical galaxies. So they are more of sort of like a transitional type. So they have the flat rotating disk and the central bulge of a spiral galaxy, but they lack spiral arms like the spiral galaxy. Now, instead of arms, they are more the outer of these galaxies are more what do you say, look alike to the elliptical galaxies. So one more thing about it is the cold gases needed for new star formations are pretty much here. It's available in these lenticular galaxies. So the ellipticals, in that respect, they are often thought to be stripped spirals, these lenticulars. So why are they stripped spirals? Clearly because they do not have arms like the spiral galaxies. They just have the bulge in the middle, which is pretty prominent. Apart from that, they do not have arms, but they do have some properties of the spiral galaxies like disk-like nature, etc. Um, but these galaxies, like the lenticular galaxies, instead of having arms and being called the stripped galaxies, they have gas removed by violent environmental processes, like because it travels through some dense plasma of galaxy clusters. So it doesn't have a necessary environment for star formations to happen. So it has mixed features of both spirals and elliptical galaxies. Hope that's clear. And plus, if you see a little buddy here on the right side, these are, it's mentioned IRR, which is obviously irregular galaxies. Now, due to very rare conditions wherein it's not able to adapt to enough angular momentum, or if it's not able to, if it has undergone some collisions and it is not able to come up to an elliptical, complete the elliptical formation of it, then it becomes an irregular galaxy due to various factors that is still under study. So irregular galaxies are also there. So these are the different types of galaxies that I'd like to show you. We have elliptical, we have spiral, we have barred spirals, lenticular galaxies, and irregular galaxies. Okay, so can someone tell me what galaxy Milky Way is?
Spiral.
You must have all seen the image of Milky Way galaxies.
A spiral with two major arms.
Spiral, but
A spiral with two major arms
mm,
is SB.
okay. So can you tell me what category it falls into here?
It falls into SB.
S
C.
SB. You mean this one?
No, ma'am, SC. Since it's only
SC.
has two major arms and it's like
Okay, you're saying it falls into SC. All right. Can you please go to Google and quickly check up the picture of Milky Way galaxy and once again come back and tell me? what it might be falling into.
Is it
According to the
just
picture,
SB?
it may fall in SB or around that. According to the picture, it
Sorry,
has.
come again, Praful.
I said, according to the picture, if I go according to the picture, it may fall into SB, but I actually said SB based on the data that was about to having two major arms and other minor arms and parts like that. So I just
All right.
predicted it based on that.
Okay, okay. Does anyone else want to give it a shot? Nimit, Anuj, Samili.
I think SB. I mean, because not because of the photo how it resembles, but because of the speed at which the momentum it has, the spiral momentum. Our galaxy is comparatively not too fast, but not too slow to be considered as compared to other galaxies, and it is in spiral, not barred. It is visible.
Okay. All right. Okay. Anyone else who would like to give it a shot? I'm just trying to search up an image for you all to.
One question I have. These
Yes,
red
please.
dots that we see, these are red giants or what?
I'm sorry, I'm away from the screen. Can I come back, please?
Yeah.
Yeah, sorry, come again. Can you repeat your question? I'm sorry. Hello?
Ma'am, I googled it. Can I say?
Ma'am, can I change
Hmm.
my answer?
Sorry, I got
Okay,
disconnected.
Praful, please.
Okay, no problem, Nimit. 1 minute, please. We'll
Yeah,
just
yeah.
complete Nimit's question, and yeah, Nimit, ask me. Yes.
Yeah, so in the image, when we zoom it, so there are red dots, a cluster of red dots. Oh, what are those?
Yes.
Red
Okay,
giants
I
or
will
what?
zoom that up for you. And mostly in ellipticals, we have low stars.
Okay.
Yeah. Okay. All right.
So from the image
Let's
that
see
we
here.
are, I am also able to get SB. Yes.
From the image, you're able to understand it's SB. Huh?
Based on this, I like to change my
But
answer.
we'll
Give
have
me
to
a moment.
consider
Give me
the
a
age
moment.
of
I'll
the
just
stars also.
1 minute. Give me a moment. I'll just zoom this out and I'll try to put in an image here. I'll just stop sharing for a moment, please. Okay. I'm just sharing it again so we can all see the same image of Milky Way galaxy and try to come up with a solution. Hope that's a big enough image. Is the image visible, guys?
Yes, ma'am.
Yes, ma'am.
All right. So this is Milky Way galaxy. Okay, so all of us are pretty sure this is a spiral galaxy because obviously we see a lot of spiral arms. Yeah. Coming to the dead center of this, we know there is a bulge, so it has to be yeah, we know there is a bulge, and but also I don't know if you guys can see that the bulge is pretty flattened out.
Yes, I want to get
Yes, ma'am.
An
thousand.
exact circle. It is flattened out more like a bar.
I got it.
Yeah, well, Google has written it very clearly, I understand. But I don't, I wanted all of us to just, connect it with the image. Um, but yeah, so if it's just a bulge, if it's not a barred spiral, then we'll have pretty distinct bulge in the middle, which is a spherical bulge or a circular bulge. But here we have a pretty flattened out bulge, which I believe if you take out all the rays of the light and all the glare that is going into the image, you will be able to see one light up spot in the middle and an extended arm. And from the end of those arms is where all the arms are starting. Do you agree?
Yes, ma'am.
So that means, coming back to our slide, Milky Way galaxy is, believe it or not, guys, is actually an SBB or an SBC. Okay. Now,
Yes, ma'am.
this from these images, you shouldn't think that, okay, since there is, you see only one arm from this end and one arm from this end, which means there are only two arms. No, that is very incorrect. This is just a schematic diagram. So just for the ease of understanding, we have put it this way. But otherwise, there are multiple arms coming out of, each end of the bar. So with our, what do you say, with the studies that's going in, it looks like an SBB or an SBC, but our Milky Way galaxy is categorized under SBC. Got it?
Yes, ma'am.
Yeah. Okay. That is primarily depending on the rotation aspects as well as the bar length as well. Okay. So yeah, so these are some factors about the shape, the population of the stars, and the dust gas contents and dynamics of these. This is a table I can give you separately, this table, or if you want to check it out from the recordings, that'll also be great. So this is all about our the Hubble tuning fork. Yeah, so if you would like to take a look here, I've already explained this. A to C sequence will relate to the bulge size and arm tightness. So the bulge size, A, would be large, and when it comes to C here, that is smaller, and the arm tightness for A would be large, as in the tightness would be more wound together. For C, it would be lightly wound together. So that's about it. Moving on, we are looking into the differential rotation part. Now, this is where we come to more theoretical aspect of these. All right. Please give me a moment. Please, I'm really sorry. I'll just 1 minute, please. Sorry, guys. Okay. So moving on to the differential rotation part, we have the first topic to be discussed is the rotation and the winding problem. So let's tackle the motion that is taking place inside these rotating disks for spirals, especially. Now, the spiral galaxy does not rotate like a single solid wheel, like how we would imagine it to be rotating. So the speed of rotation will vary depending on the distance from the center, and this is called the differential rotation. All right. So from the center of the bulge, the distance of the arms is what I mean. Okay, so we initially expect the rotation to follow some simple Keplerian dynamics, like for example, uh, like the one we see in solar systems, right? Wherein all the celestial bodies rotate around one static star. The star in itself could be moving, could not be moving. That depends, and the star will have a rotation within itself, and these Keplerian dynamics is how we would imagine it to be or expect it to be rotating. So outside the central, basically the dense mass, the velocity should drop off, and as you can see in this diagram, I mean in this formula, the velocity is directly proportional to or inversely proportional to the root of r. So that is the orbital velocity v will decrease with the distance r. Can someone tell me in one sentence what you understand? I just want to see how much that has been conveyed to you. The orbital velocity v should decrease with the distance r.
Larger the radius, the smaller the spinning velocity will be.
Exactly. All right. So as the radius increases, the speed would reduce. Okay. But within the main disk, the inner stars will complete an orbit faster than the outer stars. Does that make sense? Because inner stars would have very little distance or very little circumference to cover, wherein the outer stars would have a larger circumference to cover. So the inner stars would be highly rotating at a higher speed because obviously, according to the formula as well, the radius is less. So since the radius is less, the velocity would be high. So the stars at the inner part would have a reduced radius, which will increase the velocity of it. Also, it will, I mean, logically, if you just imagine it, uh, like let's say we are all standing in circles, right? The student standing in the inner circle would be able to run faster around the center than the student standing outside, like outer side of the circle, to take the bigger circle around the center. Yeah. So so with this idea, like just imagine painting a sort of a beautiful distinct spiral on a surface with a viscous liquid and then stirring the center. What happens? The pattern would immediately stretch and shear and disappear rapidly. Now, this is because of differential rotation. This is a simple concept of differential rotation that is applied in a lot of our day to day concepts. So, differential rotation should completely shear a spiral arm structure in a mere, like, let's say, few 100 million years. And uh, a little cosmic moment, and we observe spiral galaxies that are 10 billion years old. The arms cannot be fixed structures of the star. It'll just keep moving as these, billions of years that keeps going, but it'll take longer time for the outer stars to cover up that area, and the inner stars would do it in a faster pace. Now this will give the sort of bend to the spiral arms that you see. So let's say if everyone is starting at, and if it was a straight line, like a rays from the middle of the center, I mean, from the middle of the galaxy, obviously the inner ones will start rotating, I mean, start covering the center at a faster pace, while the end ones will take a longer time and bend towards that. So it's basically the appearance of it that is giving us the image or giving us the shape of the galaxy. Hope that's clear. So, in that way, if you look, the physical matter that makes up the arms must be constantly charging as well, or changing to rotate at a faster pace and regain charges into it, especially the stars in the inner circle. So, this will look pretty stagnant to us when we look from the outside, because obviously the light that is coming from there takes billions and billions of years to reach our eyes. So when we look at it, it looks pretty stagnant. It doesn't move, but it's actually going at different and varied speeds of light, and it's constantly changing. But we are not able to identify that change. Like, for example, I had mentioned in one of the first few classes, I guess, whatever we look into on the sky, the stars, the whatever telescopic views you have of different galaxies, like, for example, the most evident one from our night sky is Andromeda Galaxy. So, Andromeda Galaxy or different nebulas that you could take a look at, all those, excuse me, all those that you're looking at are you're basically looking back into millions of years ago, because what you see there is probably the light that reached your eyes from millions of light years ago. Okay, so what is currently happening out there, or what shape it currently has, or is that star even there? The star that you're trying to observe right now, which is visible in the sky, is that star even there right now at this point? We would never know, because if the light years take, I mean, if the light takes millions of light years to reach our eyes, we are probably seeing the light that was from millions of years ago. So what we see right, I mean, what exactly is happening there right now is probably visible to people who live millions of years ago after, right? So exactly, so it is a dynamic solution, but we are not able to identify the dynamic nature of it because of the constant moving and the light years being able to reach our eyes. So that is basically what I wanted to discuss about the differential rotation and the Newtonian dynamics in a galaxy. Yeah. Yeah. Okay. So now we had discussed about the what do you say, the density, the rotational aspects of it, and various, what do you say, some Newtonian dynamics, and how that dynamics doesn't work in real time right now when we observe it. So basically, the accepted solution to all these winding problems and density wave theory is that this theory will suggest that a spiral arm is not a line of stars. Okay, but basically, it's a persistent wave of uh, some very enhanced density, and you can imagine it more like a traffic jam in the cosmic level. So it is a wave of some very enhanced density, and this wave will keep going until it just the wave just keeps transmitting. And this what do you say, these spiral arms, or the line of stars that we may perceive it as, uh, these will orbit the center at very constant slow speeds, and the stars and gas stream into some slow moving zone, pile up, and then stream out again. So all these are due to the persistent wave that is going on from there. But again, through observations, we won't be able to come up with what happens on a live note with these persistent waves. But theoretically, this is the most, I think, most convincing or most accurate form of conclusion that we can derive from here. All right. So, yeah, this is what I have mentioned here in points. Now we have the spiral dynamics. Spiral dynamics, another version of it, or like more like a visual prominence of it. So basically, if you check some very important key to a visual effect um, is the gas that we are able to see. We are able to see some gas and dust particles. So more than the stars in itself, we'll be able to decipher it more based on the gas and dust particles. So while the stars mostly pass through some cold molecular gas clouds, and these gas clouds, which are compressed by the wave that I was mentioning, or the density wave, which is high in density, or persisting density, that is not irregular, that is not incontinuous. So this slight compressions that the waves experiences probably just enough trigger to the gravitational collapse of the gas clouds. And this trigger can possibly lead to some rapid and widespread star formations. That is why uh, the the waves of density, or the density wave theorem works only in spiral galaxies and not in elliptical galaxies, because only spiral galaxies have the ability to give rise to new star formations, and even the gas and dust particles are arranged in a more organized way, wherein the elliptical, you know how it is formed due to mergers, collisions. It is pretty chaotic, and due to this chaos that is taking place inside the elliptical galaxies, it loses the ability to form a stabilized base for the stars to form. All right, so think about what stars are born. It could be massive, like brilliant, and sometimes or mostly in these, it'll be short lived blue stars. Now, blue stars, can someone tell me blue stars mean, um, is it hot or cold? Exactly. So, in, sorry, come again?
Blue stars must be hot, right?
Yes, blue stars would be hot. Yeah, so this is one concept you will have to stick in your mind. In astronomy, astrophysics, whenever you say blue and red, you should have the immediate idea of blue means hot and red means cold. So all the red supergiants, red giants are all cold stars, and blue stars could be like white dwarfs, or all the blue stars are extremely hot, and they are not very big in size as well. Okay, so what we have here due to the density wave theory is that the stars that are formed here, or born here, are mostly short-lived blue stars. And that is of different blue types. We have, if you check the HR diagram that we had given earlier, you could have seen different alphabets mentioned down. Like there is K, L, M, N, O. So all these come under the same category. So we have O and B types of blue stars. That is just mentioning the position where the blue stars occur on an HR diagram. So O and B types of blue stars are short-lived, and there are millions of smaller, long-lived stars as well. Other than this, the crucial point is that the massive blue stars are the most luminous one, and they only live for a few million years. And they are born in the arm and they die in the arm before they can rotate out to other, or to to out, like, you know, to widespread region of the galaxies. So their intense blue light highlights the sort of compressed region, making the arms visually prominent, and they're visually prominent as in the color. The blue will be very prominent, even though the stars that define the overall mass of the disk are spread out everywhere. So the pattern persists because new stars are always lighting it up. Now, this is the main idea we use when we take astrophotographies. Now, in astrophotographies also, when we use different filters and when we try to superimpose them, if we find blue spots very prominent, then you know there could be a star that is born and died there. You know, you can come out with a lot of inference there, as in these stars could be massive but short lived, and this could be uh, what else can you concur about it? It is very prominent, and it is extremely hot, and they have a very compressed region inside, and all of that. A lot about these stars could be just identified because of the light or the color that is being prominent there. Now, in astrophotography also, we take our basic photographs of the transit or of different positions, like over a few years, over a few hours, we would be taking it all in black and whites, in certain gradients, and then we superimpose them with certain filters like UV filters. For green, we have another filter. We have infrared filters. We have other blue filters. We have a white filter. We have plain black filters. So all these superimposed, and then you get a sort of a superimposition where the light that are strongest would pierce through all the filters and gets covered only in certain filters. So, with the intensity of those lights being covered there, we identify what is more prominent where. So, hope you have got an idea about this. Okay, like if we were to check bit by bit on this image. So these outer rings or the outer arms is where you see the most compressed region, wherein some luminous blue stars are born, and they are short lived and they die around the same spot before they can, you know, scatter out into the different parts of the galaxies. And once they die, they will undergo supernovae and nebulitic features, and they can go into being a neutron star depending on the massivity, all of that. And these supernovae can probably, what do you say, exist around the outer rings of, or outer arms around the outer surfaces of the galaxies. Now we have some short-lived, I'm sorry, I think this is a typo wherein it's blue stars. It's a typo, sorry. Now we have some short-lived blue stars that is definitely going into supernovae existing in the inner arms. And we have older, lighter, some yellow reddish stars. Those are basically yellow stars, are obviously main sequence stars, and some red giants, red supergiants in the orbiting in the inner arms of the galaxies. And we have sun-like stars of lower mass, that is definitely main sequence stars of lower regions, or main sequence stars that are just come out of the protostar level, as in they have not they have crossed just the birth and a little bit forward after the birth. So those kind of stars would be highly scattered out of the galaxy due to obviously the having the lower mass and not enough mass to be in the galaxy circle in the spinning. So that is about the spiral dynamics that takes place here. Moving on, oh, it's already time. I hope, I request everyone to stay back for another 15 minutes if that's possible. We'll finish up today's part and we'll move into the next session. Okay, so coming to it, so we have discussed first section, we have discussed about the types, the Hubble natures, different galaxies, how they form their shape, how is elliptical galaxies and spiral galaxies form, how are they different, what is coming in the transitional phase of these galaxies, and even in the spirals, how the bird have come up. And we've even looked upon what kind of galaxy we live in. And after that, we have come into some theories wherein we discussed about the rotational aspects of it, the density wave theory, how wound up these spiral galaxies can get, and what about the winding up can determine what, and how the stars are scattered in these galaxies, spiral galaxies, etc. Now we are looking into a little bit about dark matter. So I believe someone had mentioned about dark matter um, to be taken up as well. So I believe there are some aspects of dark matter that is being covered here. If you would like any more topics about dark matter or any more, I think we'll have in the upcoming session as well. We'll have some of the dark matter topics. But yes, so here we'll be talking about dark matter and how this is all linked. So, evidence for dark matter. So we have had some clues, and how we built it up from there. So now dark matter is basically, I believe, at one point of the last century, it was a very mystical topic. Like, it was very mysterious. People couldn't come up with what a sort of empty mass region could be. All right. So the discovery was originated from a very simple question: is there enough mass to keep the largest structures from flying apart? Can Does anyone want to put in your thoughts here? How could
Ma'am, can
you
you repeat?
probably? Sorry, come again.
Can you repeat?
Yes. So while they started studying about dark matter, right? One of the first questions scientists had tried to encounter was, is there enough mass to keep this largest structures in the outer space from flying apart? Like, how much of a mass is required for a large structure, like, let's say, like the biggest star or biggest celestial body, to keep them together? How much of a large mass is required? I mean, is there enough mass as such to keep them together? If you would like to get into some crazy discussions here, put in your thoughts. That would be cool. All right.
As
Okay,
in
I'll take.
enough mass to um, stop the motion at which each galaxy or the planets are moving or
Sorry, come again.
flying apart. I mean, enough mass related to stopping or maintaining the continuity of the galaxy or the solar system moving,
More like maintaining.
maintaining. Okay.
Yeah.
I think it is a kind, not exactly maintaining, but
Mhm.
slowing it a little bit down, I think. I mean, the expansion.
All right. Yeah. And what do you think the source of all these masses could be from?
Um, the existence of dark matter, maybe.
Something invisible.
So, when this question was first raised to scientists, they didn't know something like a dark matter existed. So, what do you think their idea of sorting that question could have been?
The the
Assume something.
sorry.
Sorry, come again?
Let's just, and you asked about thinking, so I just said, let's just assume something if there is nothing, something we can't see. Like we talk about higher dimensions, but we can't observe them because we are three dimensional. Same like
All
that.
right,
We can't see those also. So that's
got
exactly.
it.
I think
Okay.
the energy equation where if if all the energy is converted into mass or the energy again, so there must it will must be equal, because energy, it cannot be created or destroyed. So
Mhm.
if there is something which is stopping, then of course there will be the not the equation will not match to the equilibrium of what expected to be in the LHS or the RHS.
Exactly. Perfect. Yes. It's all about the equilibrium, basically. So, if you want to stabilize something with enough mass, you need to make sure that the equilibrium of it is equivalent on both sides of the equation. Or, in other words, like in real life, you need to make sure that whatever is affecting and whatever is being affected has to be in an equilibrium. Right. So, with that thought, we'll just we'll just see how they came up with the dark matter. So the first clue came out in 1933 by an astronomer named Fritz Zwicky. So Fritz Zwicky was studying a cluster called the Coma cluster, and Fritz Zwicky used something called a virial theorem. All right. So a virial theorem, it relates to kinetic energy and gravitational potential energy, wherein it had to be balanced between the energies. And this virial theorem later became like one of the cornerstones of gravitational physics. So, simply put, for a system to be stable, the kinetic energy, or how is the kinetic energy formed? Kinetic energy is formed due to the motion of certain bodies. So, the kinetic energy or of the motion, or kinetic energy caused due to the motion of its components, must be balanced by gravitational potential energy. So both of these have to be in equilibrium for the mass to act where it has to act, right? So with this virial theorem, Zwicky was trying to come up with something that he observed in the Coma cluster, and this is where he thought, okay, virial theorem is perfectly explained in this cluster. Now, Zwicky measured the speeds of the galaxies in the Coma cluster and found they were moving incredibly fast. So they had far too much kinetic energy because the movement was extremely high. So there was a lot of kinetic energy being formed there. And this kinetic energy could look like this is more than what the mass of that cluster can hold. Okay. So he concluded that the cluster needed 10 to 100 times more mass than that was visible to hold in itself together. And he called this mass as the missing mass, or uh, this mass to be something like a Dunkel materie. So Dunkel materie was the term given to dark matter before it got the name dark matter. So he called it the Dunkel materie. So there has to be a Dunkel materie that will give enough mass. So what happens is, in short, to put, he saw that the cluster was spinning very fast or going in very high speeds. All right. So he knows, okay, there is a lot of kinetic energy already being generated because of the motion of the components. But for um, for for the visible part of the mass to contain it, the mass of the entire cluster, he figured out that theoretically, or at least through studies, this particular mass of this entire cluster cannot be running with just this much kinetic energy. I mean, this kinetic energy is pretty huge. It is spinning very fastly, or it is moving very fast, but that even that much kinetic energy able is not theoretically supposed to stabilize the mass of this entire cluster. So he assumed, okay, so if kinetic energy has to be equivalent or has to keep the mass on the other side in equilibrium, then if this mass is like 100% and this kinetic energy is, let's say, an 80%, if it has to be in equilibrium, there's a 20% missing. So this 20% has to be added with kinetic energy, and that 20% he couldn't understand, or he couldn't identify what that was, and that 20% he named as Dunkel materie or dark matter. All right, so hope you have understood what Dunkel materia is, what dark matter, how dark matter came into existence. There's not much to explain what dark matter is, but I can only explain how it came into effect and some features of it, maybe. So it was the coma cluster. It was Fritz Zwicky who was learning about it, and he tried to apply the virial theorem, wherein he understood that there was kinetic energy, which was supposed to keep the gravitational potential energy in equilibrium. And he tried to apply the same there. And he found that there was a lot of kinetic energy, but there was a lot more mass in the cluster. And this mass, if it has to be in equilibrium, there has to be some extra mass or some extra kind of generation that happens along with the kinetic energy. And that void or that empty space was filled up with a Dunkel materia or a dark matter. So that's how dark matter came into existence for the first time. Hope this is clear.
Yes, ma'am.
Okay, coming. So, although initially ignored, this evidence was dramatically confirmed later, like much, much later. So, when Fritzwicki told about his or published about his idea, it was not widely accepted. Okay, so it was ignored. Nobody believed in dark matter. They told everything is science. It has to be explained by science. So it was not receiving a sort of recognition that he expected. But decades later, when we started having a method called gravitational lensing, through gravitational lensing, we have confirmed that, okay, dark matter exists. Without dark matter, you can't keep the kinetic and the gravitational potential energy in equilibrium. Right. So, since mass of an object or mass of this some cluster warps space time, as we know in the warping of space time, etc., the light from background galaxies is bent to the total mass of the foreground cluster. You must have seen that in images of black holes. So in black holes, you might the most, I think, most popular image of black hole is one black circle with golden light around it, and there is a ring-like thing that's going. You must have noticed. Okay, let me try to get that. That is probably one of the first images of black
Um,
holes that you have
Uh,
seen in your
are you
life.
are you talking about the real one or like the imaginary in which the ring backward part of the ring gets sewn on the front?
Yeah, exactly. I will just, okay, this is another image I can show you. This is, I think, more better to discuss. Yes, give me a moment. I'm just sharing it once again. Hmm. Yep. Yeah. So this is one kind of image of the black hole. That is, this is basically through methods like gravitational lensing, etc. So these are like dotted diagrams that we are able to get through like initial observations. So this black hole is supposed to be like a circle, but if you see, there is like a ring like thing that is going on through here. I think my cursor is not visible, right? Yeah, so there's a ring like substance that is appearing here, which is not allowing the whole circle to be seen. This is basically like if you imagine this whole circle is in a paper, this paper, if it bends towards you, how would you be able to see it? That's exactly what is happening here. So the space time is warping and the mass is bending the light towards you. That is because of the delay and apparent what do you say, apparent falling of light onto your eyes or onto the observer's eyes. So that is what is happening here. So I hope you're able to connect it here.
Yes, ma'am.
Yes, ma'am.
Yeah. Okay, so if I were to show you, no, I don't think I have anything to show you here physically. Oops. Okay. Never mind. I hope you guys have understood. So it is a full circle, but if this part of, okay. Um, do I have a pen here? Oh no, I do not have a pen here. Yeah. So let's imagine there is a big circle here, okay? In this sheet of paper, there's a big circle, and I bend this towards you. So what do you see? You see this edge as well as half a circle. Yeah. So that is exactly what's happening to a black hole when we try to attain the light from that surface towards us. So the mass warps the space time and the light bends and it reaches to your eyes as if it's a half circle and the light is bending towards you. Okay. Yep. So, yeah, so it was through gravitational lensing that later people could, much later after the scientists, after Zwicky could try to come up with something. After that, I think decades later, we have a lot of astronomers confirmed the kind of idea that was put forth by Zwicky, and that was through gravitational lensing. Now, as I've explained right now, the Mars was warping through space and time, and the light from the background galaxies by the were bent by the total mass of the cluster that was around it. The amount of bending we observe is always much stronger than the visible mass. Okay, so that bending we observe to be strong is because of how sensitive our observatory equipments, or how sensitive our eyes are, or the observer is, or how sensitive the atmosphere through which this light passes to reach our eyes also are. Now, the most compelling example is here the cluster that you see, where basically a collision separated the dark matter, which did not interact with each other, from the normal gas. So, allowing us to see the dark matter distribution directly through its gravitational effect. Like, for example, if you can see the sort of the dark matter that is going on here in blue, and that dark matter did not interact with the rest of the gases, and this is due to the gravitational effect that is observed through gravitational lensing. So this gravitational effect is basically a big confirmation that the dark matter exists, and it is mostly non-baryonic. So non-baryonic is basically it is not completely apprehensible, and it is just there to balance the sort of equilibrium that we require. And this dark matter, whatever it goes into, how the energy is conserved within it, is still, there's a lot more to research and understand in that. So yeah, so this is about some first clues of dark matter that we have come up with. Moving on. Yeah. Now something about the rotation curves of dark matter. Okay. So so if you remember, Zwicky had provided, Fritz Zwicky, the first astronomer back in 1933, he had provided the first clues in clusters and the very definitive evidence for dark matter back then. And this this evidence came from pioneering work of someone called Vera Rubin. And Vera Rubin means an unavoidable evidence, and this was coming across in 1970, named after the group of people who worked into it. And here in Vera Rubin, it was looking into individual spiral galaxies, and even the person who headed the team, she asked the same sort of fundamental questions, like, does the gravity match the motion? If it doesn't match, then what could be an extra fitting to keep this in equilibrium? So she asked the same question as Fritz Ricci asked. So using some sophisticated techniques back then to measure the Doppler shift of gases, or the apparent shift of gases, gas clouds, from some visible stellar disks. She plotted a rotation curve, and yeah, she plotted some rotation curve. I do not have the rotation curve right now. Uh, but okay, I think I should probably explain this with a rotation curve. That will be more easier to understand. Sorry. Okay, basically, I will get a rotation curve next week, next session. So there was a certain colored line, like we have yellow and blue colored lines. Now, the yellow colored lines in the rotation curve, which I'll be showing you in the upcoming session, I'll just give you a gist of it. So the yellow dashed line will show the expected behavior. Like, wait, I'll just try to check if that's available on Google. I may have to go back and check some papers. Mm. All right. Um, Enough to understand on explanation, I will get um in the next session. But okay, so we had a certain line that will show the expected behavior based on some visible mass, and like in the solar system, for example, the certain speed should drop off dramatically once the orbit is outside the bulk of the mass. So that was the expected behavior. Now the velocity doesn't drop off. It doesn't. It sort of stays flat. Now this was the contrary that came in. So the expected behavior was that the velocity drops off when it is outside a certain mass. Okay. But another line it had another line of blue color. Now this blue colored line would show that the velocity doesn't drop off as expected. It just stays flat, it just stays constant, or even increases slightly sometimes into the galactic suburbs. Now this is sort of a massive violation of Newtonian gravity, because obviously when it goes out of the mass, out of the influence of mass, there shouldn't be a velocity existing. Velocity should just drop down drastically, and it shouldn't have any sort of speed that it can undertake. But this was against the common expected behavior. And Newtonian gravity basically predicted by visible matter alone, and for velocity to remain flat, the amount of mass enclosed within that orbit must keep increasing, or increasing linearly, or at least increasing to a point wherein the velocity can keep flat. But here, as very opposed to what we expected, the velocity didn't drop, velocity just stayed flat, which is unexplainable in that circumstance, because that is totally unexpected. Now that was the rotational curve. I forgot to put in the image here. I will put it up in the next session, and I'll once again discuss the slides with you. Now, through the rotation curve, we have come up to a very inescapable sort of conclusion. So, this inescapable conclusion is that every large spiral galaxy is embedded in sort of a very vast, spherically distributed um, structure that is also not luminous. And this spherically distributed structure, wherein all these masses are accumulated, is called the dark matter halo. So the dark matter halo is much, much larger than the visible disk. Um, and this is what provides the gravitational pull to keep the stars orbiting at such high speeds. And this is why dark matter, which is sort of non baryonic and only interacts through gravity, and sort of is the whole central to forming galaxies or galactic formations. Now, this material, which makes up about 85% of all the matter that we see, access because, as you might have heard, all the gas particles, dusts, and stars, all the celestial bodies, all of these in the galaxy only constitutes 15%. Now, what about the rest 85%? So, we are trying to come up with an understanding where the rest unexplainable 85% is dark matter. Now, that dark matter acts as a sort of cosmic scaffolding upon where we have the sort of beautiful light structures we see are built. Now, this is all about the rotation curves and all about the dark matter halo. This last two slides I will be explaining once again in the upcoming session with a sort of rotation curve where you can understand easily. Now, with this, I am calling it a day for the part one of this session. And that's about it. If you have any more questions, you may ask. If not, we will call it a day.
As it is raining too heavily, so my voice might not be clear. But
Problem. Anuj, I can hear you. Tell me.
okay, so I have one question that, as it
Yes,
is mentioned, how you said that the universe is mostly what matters, actual matter which is visible, will constitute still 15 to 10% of the whole
right.
matter.
Yeah.
So the rest is 85 to 90 dark matter. But the
Yes.
elements, the maximum element the universe holds is mostly of hydrogen.
Yes.
So how
And
much?
helium. Yeah.
Yes, and helium. That is the byproduct or the next stage of what hydrogen combines. So
Yes. Yeah.
how much? out of the 100%, if 85, 90 is dark matter, how much does the hydrogen constitutes in this
Hmm.
percent wise?
Oh, I wouldn't know it specifically for hydrogen or the gases in general, but what studies are showing is that the 15% has all the gas particles,
Mhm.
or the atmospheric composition uh, is within the 15%. So it is way less than 15% for sure. But hydrogen, I would take as a pretty big composition in the 15%. So I would probably say that is an 8 plus percentage is just hydrogen and other gases that constitutes the atmosphere or
Okay,
the composition.
okay, ma'am. Any task or anything you would like us to research on for the next session discussion?
Not in this class. I have a task for you all in the next session,
Okay, ma'am.
because the part two of this will have some more contents. With that, you will be doing a task.
Okay, all right.
Yeah. I've been giving relatively very few tasks these days because I was trying to give enough time for you all to complete your previous tasks. Now that I see that most of you all have completed a lot of it. So from the upcoming session, you will have more or less at least one task a week. So then I think in another 1.5 weeks, you will have your minor project two as well coming up. So this week, the last week was pretty, what do you say, relaxed, I guess, from the astrophysics sessions. I'm not sure if you had other sessions tasks, but from the astrophysics, nothing was there in the last week. I assume, yes, there weren't any. So in the upcoming week, you will have one session, but one task. But the next week and the next to next week, we'll have a pretty hectic week. We'll have minor project two, which is basically presentation. So each of you will be presenting, and you'll have to do some research, some heavy research on that. So yes, so chill for this week, I guess.
Okay, ma'am.
Yep. All right. So if we don't have any more questions, let's call it a day and have a wonderful weekend, y'all. Happy Saturday, happy Sunday. All
Yes,
right,
ma'am.
guys. Thank you so
Sure.
much. Good night. Bye bye. Bye, Praful. Bye, Brishaketu. Do we have any questions? All right. I'll take that as a no. Praful, do we have you here? Okay. Okay, I'm removing you. And Brishaketu, do we have you here? I guess not. Okay, I'll remove you as well.